All right, so let's see if this works. This is Bill Miller. I'm going to try and do some journal article reading the way that I was taught how to do it. And what I've got here is I've got an article, Microemulsions of Nonionic Surfactant with Water and Various Homologous Esters, Preparation, Phase Transitions, Physical Property Measurements, and application for extraction of tricyclic antidepressant drugs from aqueous media. Now, this is an article that I'm interested in reading because I'm interested in microemulsions. I'm interested in making them from non-ionic surfactants. I am not interested in making them with water, as we'll see. But this was one of the closest things I could find to the direction that I wanted to go and learn about and possibly do. And the first thing that I do, or one of the first things that I do when I get an article, is I go ahead and write my last name on it, and then I write when I got it. So this is going to be 2/26. That's February 26th of 2026. I don't write the date, just the month and the year. And very much so, what I do is I read along. So I read along to, and like out loud, like literally. And I know this is how my advisor and I, we would take turns reading sentences or paragraphs, depending upon exactly what we were looking for from the article. And let's go. Oh, and so it's okay that there are a lot of words that we don't know. There are words that I don't know in this article, though I do know some of them. And so I'll be more of the advisor role in this. But let's start with the abstract. The abstract is, of course, the summary of what we're doing, why we're doing it, and what the results are in one paragraph, something that will then take 30 pages in this article, so including references. I'm going to go ahead and do an extreme zoom in here. So hopefully the words will be bigger. Microemulsions are nanocolloidal systems composed of water and oil and a surfactant, sometimes with an additional co-surfactants. Now, if you know what my lab does, you know that my lab typically does binary solutions. That's solutions with two things in them. And already we've got water and oil, a surfactant. We've got at least three things, and sometimes an additional co-surfactants. So that's up to four things. And so one of the things I'll say is this is a step in a new direction by having clearly three things, sometimes called a ternary system. Ternary means three, more binary, ternary analogy. And it is my plan not to add a fourth because three is enough. But we see some terms here, a surfactant. So if you're reading along and you see this word, you might want to look it up. I happen to know what a surfactant is. A surfactant is a surface active agent. That means something that's active at surfaces. And we'll see that a surfactant, and I might just back up a little so I got a little more room for my pen there. Hopefully that's not too bad. So let's just write surface active agent. And again, if you look this up, I imagine, or I do happen to know what this one is a something that's active at surfaces. And sometimes you'll have, very typically, an air-water interface. And then oftentimes, in what we're going to be doing, there will be more generally a polar liquid and a non-polar liquid. And that's where we're going. And that's what a lot of microemulsions are. They're not so concerned with the air-water interface, they're concerned with the non-polar liquid, polar liquid interface. And for example, water and an oil would be polar, non-polar. And a surface active agent, very like you might imagine, has a polar part and a non-polar part. And it just so happens that when these molecules with polar and non-polar parts go to an interface, where an interface is the boundary between the non-polar and the polar liquid, they will go the non-polar part in the non-polar liquid and the polar part in the polar liquid. So polar, non-polar. That's a little hard to read, but that says non-polar and that says polar, and that's the same thing we're drawing over here. That's what a surfactant or a surface active agent is. And it turns out that in one definition of a microemulsion is, so we haven't talked about nanocolloidal yet, but we can, we'll talk about that in a minute, composed of water, an oil, and a surfactant. So a microemulsion can be made from or is a water, an oil, and a surfactant mixed together. Very basic. A nanocolloidal system, nano of course means nanometer, colloidal means colloids, and it'll turn out that nanocolloidal in this case means that the features in the non-polar liquid, polar liquid surfactant can be on the order of nanometers to tens to hundreds of nanometers, but definitely in the nanometer range to be a microemulsion. Okay, so I would say we've sort of talked about the first part of this abstract, which have found a wide range of practical applications, including the extractive removal of contaminants from polluted water. That sounds very important. In this study, microemulsion systems, including a non-ionic surfactant called Bridge 30, and we might want to find out what Bridge 30 is by looking it up. We know it's non-ionic and it's a surfactant so far. Water and esters selected from two homologous series of C1 to C6 alkyl acetates. And so esters are going to have carbon, oxygen, oh, I don't think that's right. I think that's what they have, though. I thought those were ethers. Well, we'll have to figure out what esters are. It's been a while since I worked with esters. Selected from blah, 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 with C1 to C6, so there's going to be 1, 2, 3, 4, 5, or 6 alkyl. Alkyl means alkane or single bonded carbons, acetates, and ethyl carboxylates. Oh, okay. So an ester must be CO carbon double bond O in the middle of a molecule somewhere. That's my current guess. And it must be, yeah. So esters selected from C1 to C6 alcohol acetates, like acetic acid, and ethyl carboxylates. That'll have ethyl on one side and C1 to C4 on the other side, I'm guessing. Respectively, we're prepared. We'll figure that out. I have to look that part up too. We're prepared by the surfactant titration method. This is one thing that we're very interested in, and this is one of the main reasons we're reading this paper, is because we want to do the surfactant titration method. phase transitions leading to the formation of Windsor 1 and Windsor 2 and Windsor 4 microemulsions were observed and phase diagrams were constructed. This is all based on the surfactant titration method, and we want to make these phase diagrams. The dependencies of phase transitions on the salinity just means salt amount. And does it say, it says water up here. It says aqueous media. It hasn't said anything about salt before, but salinity is salt solutions. And pH and the addition of isopropanol, that's 2-propanol, as a co-surfactant were also investigated. Some physical properties, namely density, refractive index, we're a big fan of refractive index. We can measure that nicely. Electrical conductivity, dynamic viscosity, well, we can measure viscosity as well. And particle size, we cannot measure that. Were measured for a selection of Windsor 4 microemulsions. We'll figure out what those are soon, hopefully, providing further insight into some other phase transitions occurring in the monophasic, mono means one, phasic means phase, domains of phase diagrams. Finally, Windsor 2 microemulsions were tested as extraction solvents for the removal of 4-tricyclic antidepressant drugs from aqueous media. That sounds really cool. I hadn't thought about what these were going to be used for when I got this because it mentioned the surfactant titration method, but they're going to try and extract antidepressant drugs from water, which if antidepressants were in drinking water or wastewater, you might want them out. Propyl acetate, bridge 30, H2O microemulsion. So H2O is our water. Propyl acetate is our oil, and bridge 30 is our surfactant. So this is a 3-component microemulsion, no co-surfactant. Provided the best extraction yields, greater than 90%, the highest Nernst distribution coefficients. I don't know what that is, but I know what the Nernst equation is from Chem 401, and a large volumetric ratio of almost 3 between the recovered purified water and the resulting microemulsion extract. Okay, so that suggests to me that you've got 3 times the water being purified as the microemulsion that contains the antidepressants. That sounds interesting. Increasing the ionic strength, salinity, so ionic strength, I don't know exactly what it means. I learned about it once in physical chemistry. Oh, we're still on screen, good. But basically, if you add salt, there are more ions, the ionic strength of the solution increases. Or the pH of the aqueous antidepressant solutions led to an improvement in extraction efficiencies approaching 100%. Nice. These results could be extrapolated to other classes of pharmaceutical contaminants and suggest ester and non-ionic surfactant-based microemulsions are a promising tool for environmental remediation. I still don't know why they chose esters. Maybe the tricyclic antidepressants have esters in them and like dissolves alike. Potentially, I don't know. Okay, so that was the abstract. We found some really the important things reading forward that we want to make sure we get are the surfactant titration method, refractive index and what it says about how to test a microemulsion for it, and and this Windsor 2 and Windsor 4, which we'll talk about more. All right, and that's all just the abstract. Now, let's take a minute And I have to admit, I did do this, but let's take a minute and flip through it a little bit. So we'll read the introduction because, but here's Windsor 1, 2, 3, and 4. We've got oil, microemulsion, and water, which in this don't show up very well because I don't have a color printer. Somewhere over here, I've got the article. Right. Okay. So this is oil, the top one, and this is microemulsion. And microemulsion, I'm going to do micro, so lowercase mu and capital E. So this is going to be microemulsion. And so a Windsor 1 type microemulsion has microemulsion with oil on top. Typically the oil is less dense. Then it's hard to see here, but there's 2 here. And Windsor 2 is going to be water, microemulsion on top, water being the most dense. Then we've got water, we've got microemulsion, and we've got oil. That's 3 phases. That's a Windsor 3. And in a Windsor 4, let me just double check here. Yes, we've got all microemulsion. So, and we've already talked about Windsor 2 and Windsor 4s. And this is just me filling in what would be clear if we had a color printout. And then I like to look at the pretty pictures. This is going to be a phase diagram. In a phase diagram, you've got, there we go. You've got, this is a ternary phase diagram. It looks like a triangle. We've got whatever ester we're talking about. We've got water, and we've got bridge 30. So this is surfactant. This is water, and this is oil. I'll put oil in quotes there because it's not truly an oil. It is the most non-polar thing. And then let's see. As you can see, it says bridge 30, 100%. And so this is increasing bridge 30. This is increasing water. And this is increasing ester. And so that means, let's see if I can do this right, because these are going to be, I think, look at that. There's another one down there. More on the next pages. And so let's spend just a moment talking a little more about this. So if I'm right here, then I have 0.75. Oh, and these are all weight by weights. So otherwise known as weight fractions. Which is an older term because these are really mass fractions. All right, so if we're right here, then we're on, we're at the 75 or 0.75 fraction water. Oh no, bridge 30. This is why I do this, is because I have a hard time with this. We are at the, so 0 line, so on this direction with the 0 line for the ester. So 0 ester. And that means we're at 25%, so 25% water, or 0.25 water. So 25% or 0.25 fraction by mass or weight, water, is this point right here. And so it's like we're on, so this line is for bridge 30 going to 100%. And then you have to see where you are on this line for the water. And then here, you're at the 0 line. Oh, so I guess, and again, I've worked with these before, but maybe a good way to do this is, let's see, so here's the bridge 30. So you're going from here to here. So you're looking at the 0.75 line. You're going from, for water, here to here. So you're going to the 0.25 line. And here you're going from here to here, and you're on the 0 line. I don't know. Maybe that makes sense. I'll have to keep working with them. But let's do an example. So let's do this point then. So this point, and we'll call this A, and we'll call this B. So this is A over there, right? And just like literally, this is, you talk through it with people or you talk through it with yourself. And let's see, so hold on. Oh yeah, everything's good. So that's B. So according to this system, let's do, oh, so we're on the bridge line. Bridge, we go up. We're at 50%, 50%, let's see. Yep, 50%, or 0.50 bridge 30. Sorry, you couldn't see that when I wrote it. And then water, we go from here, go here, and this is, I guess, 12.5%, so 0.125 water. And then for ester, we're on this line, go over to the ester. It's halfway between 0.25 and 0.50, so it's 0.375 ester for part B. So yeah, that does seem to work out pretty well. And again, I have a black and white printout, but you can see there's a bunch of 1, 2, 3, 4, 5, 6 carbon acetates. And so the C1 to C6 acetates are all on here. And at least for this initial reading of it, they're all relatively in the same close. Oh, and these are W2s. And if we come down here, it says Windsor 2 curves of ternary systems incorporating water, bridge 30, and alkyl C1 to C6 for A, temperature 25 degrees Celsius. And then this picture is going to be B, which is Windsor 4 curves for the same thing. But let's just, so we're still up here, and this is our first phase diagram in this article. And there are 1, 2, 3, 4, 5, 6, and then some bar graphs, which you don't necessarily oftentimes see. This is a very long article. We won't cover it all tonight. And in fact, what I'm going to do is this is going to be part 1 of the video. We'll start on part 2 next. That's not what we wanted to do.